Welcome to the TS session for week 2. So in this week, basically, I'll try to discuss few concepts which will be associated to uh, one like associated to Schottky diode, surface states, and all that. So I like whatever assignments were given. So if you see the today's say, I mean, what's today's session, it will be easier to solve those questions. So I'll just share my screen quickly. So it's basically like you take a crystal and like how the atoms are basically spaced and in a crystalline structure and how it looks basically. It's basically a order structure, right? So we have some surface states that are found at the surface of the material. They are formed due to the sharp transition from solid material that ends with the surface and are found only at the atom layers closest to the surface. Okay, so the termination of material with the surface leads to a change of the electronic band structure from the bulk material to the vacuum. So in the weekend potential at the surface, new electronic states can be formed. So these are called the surface states, as you know. So according to the like Bloch theorem, the eigenstates of single electron Schrodinger equation with a perfectly periodic potential, a crystallar Bloch waves, right? So let me turn on the cursor so that you can see. So this is my Bloch wave function. In K, these are the indices. So psi n k equals to e to the power I k r u n k r. So it has a periodicity, this wave function. So this is very important formula. Write down this thing. It will help you to solve some of the questions. So here you can see that this u in k r is a function with the same periodicity as the crystal. Okay. So and here is the band index and k is the wave number. So the allowed wave numbers for a given potential are found by applying the usual Born-Von cyclic boundary condition, right? So the termination of a crystal, that is the formation of a surface, obviously causes the deviation from perfect periodicity. Consequently, if the cyclic boundary conditions are abundant in the direction normal to the surface, the behavior of electron will deviate from the behavior in the bulk, and some modifications of the electronic structure has to be expected. Okay. So you can see the figure. Here is a potential profile, right? And A is the interatomic distance. With A, so basically if you put UKR plus A, that will become U in KR. So both are equal because of this periodicity in the crystal. Here is the sharp transition that you can see from this inner state to the vacuum. It is coming out. So here is a huge jump of in the potential profile, right? That is causing a transition. Now, like a simplified model of the crystal potential in one dimensional can be sketched as shown in the figure one. This is figure one. So in the crystal, the potential has the periodicity A. Okay. So the crystal, it has a periodicity A. Of the lattice while close to the surface, it has to somehow attain the value of the vacuum level. The state potential shown in the figure one is an oversimplification, which is mostly convenient for simple model calculation. At a real surface, the potential is influenced by image charges and the formation of surface dipoles, and it rather looks as indicated by the dashed line. Okay. This is a real wave function. This is crystal and this is vacuum. So it is basically reflecting the information how the wave function is basically changes. So you can see outside the crystals changing, decaying exponentially, the magnitude, right? So basically, if you do the psi square, what information does it gives? It tells you the probability of finding a particle at a particular positions, right? So psi xt, it's a wave function at a particular position and a particular time. How it's basically evolving over a certain position and time. That's what it tells you. Yeah, so the state potential shown in the figure one is an over simplification, it's, which is mostly convenient for simple model calculation. At a real surface, the potential is influenced by image charges and the formation of surface dipoles. It rather looks as indicated by the dashed line that you can see over here. Okay. So given the potential in the figure one, it can be shown that the one-dimensional single electron Schrodinger equation gives two qualitatively different types of solution. So the first type of states extends into the crystal and has a blocked character there. This types of solution corresponds to the bulk state, which terminates in an exponentially decaying tail reaching into the vacuum. So, and the second, I mean, that's figure two. So that is going to say this is the first type of states that's basically extending into the crystal and has a block character. I mean, block character means this equation needs to be satisfied over a certain period. I mean, with the lattice crystal. That's what the block theorem states, right? So this type solution corresponds to the Barn state, which terminate in an exponentially decaying tail reaching into the vacuum. So once it reaches the vacuum, this portion, no, it will decay further. That's what it has been. It has been shown here. There's a second type, like see in the figure three. Okay, that decays exponentially both into the vacuum and the bulk crystal that you can see. Right. So this type of solution corresponds to the surface state with a wave function localized close to the crystal surface. So you can see also it's decaying exponentially inside the crystal. So the first type of solution can be obtained for both metals and semiconductor. Uh, in semiconductor, though, the associated eigen energies have to belong to one of the allowed energy bands. The second type of solution exists in Fermi energy gap of semiconductors as well as in local gaps of the projected band structure of metals. It can be shown that the energies of these states all lie within the band gap. As a consequence, in the crystal, these states are characterized by an imaginary wave number, leading to an exponential decay into the bulk. Okay. So next, please listen this part very carefully because this will tell you how the surface states are. Okay. This is the typical band structure in E versus K in E K diagram. So how the block state will be that I'll show you. So this is like the nearly free electron approximation. Okay, that's very important. What do we mean by that? So the nearly free electron approximation can be used basically to derive the basic properties of surface states for nano gap semiconductor, right? The semi-infinite linear chain model is also useful in this case. However, now the potential along the atomic chain is assumed to vary as a cosine function. That is Vz. Okay. You can see V is exponential of I 2 pi z by a plus exponential of minus I 2 pi z by a. So this is imaginary part. I mean, two parts are there that you can see. So this will give you this thing 2b cos 2 pi z by a. No, actually, it should be written like it's written wrongly. It should be I times like cos theta plus I sin theta. You know that it gives you to I mean e to the power I theta from the Euler's formula. Actually, it's written bit incorrectly. Uh, Sorry for the mistake. Whereas the at the surface, the potential is modeled as a step function of height v naught. So the solution to the Schrodinger equation must be obtained separately for the two domains. Like there are two domains, right? One is for z less than zero, another is for z greater than zero. So in the sense of nearly free electron approximation, the solution obtained for z less than zero will have plane wave character for wave vectors away from the Brillouin zone boundary.
because virial zone you know, right? That is in the case space, it will be the first virial zone the occurs at plus minus pi, and second virial zone plus minus 2 pi by a, and so on. That's how it basically goes on. Okay. So that's how we satisfy the periodic boundary condition, where the dispersion relation will be parabolic. So as shown in the figure 4. কিছু এগুলো কিছু মনে বুঝবে উপর ফেলে বুঝছিল বেশি স্পিডে বলবো সার্ভার না বাড়া This potential, yeah. This part was already mentioned, and this is at the Brillouin zone boundary, right? Where the dispersion relation will be parabolic as soon as the figure 4. So at the Brillouin zone boundaries, the Bragg reflections occurs resulting in a standing wave consisting of a wave with the wave vector k equals to pi by a and the wave vector minus k equals to pi minus a, right? So here you can see, let me turn on the curves. Exactly. So this is g equals to 2 pi by it's a lattice vector of the reciprocal lattice, right? You see the figure 4 over here. So since the solution of the of interest are close to the Brillouin boundary, we set it like k equals to k perpendicular equals to pi by a plus k, where k is the small quantity. So the arbitrary constants AB are found by substitution into the Schrodinger equations. This lead to the following eigenvalues. So if you solve that, you will end up having something like this. You will find the eigenvalue which will be related to the potential, the wave vector, and some other factors parameters as well. So this demonstrates the band splitting at the edges of the Brillouin zone, right? Which is very important. Where the width of the forbidden gap. I mean, forbidden gap is the like a region where no states can exist, literally. So that means the density of states inside the forbidden gap will be zero. So here, what is the width of the forbidden gap? It's basically according to the whatever parameter curve value is given. Based on that, the forbidden gap value is 2v, I mean, given by. It's a given condition. So the electronic wave functions deep inside the crystal. So why I'm telling you all this? Because this formula will give you some rough idea how this can like band split happens in a crystal at the edges of the Brillouin zone, and how it will be related to the width of the forbidden gap, the potential. So this is very important regarding the surface stress and all that. So this, please note it down so that you will be able to solve some of the questions. So these concepts is very, very important. I'm not sure whether this has been already taught you and or not. So that's why I'm basically telling you again and again so that it makes your understanding very easier, or so it on the other hand clears the concepts. So that's why it's very important to understand these things first rather than jumping into some direct consequences or questions. So if I clearly, like, if I'm able to explain you, or you will be able to understand all these concepts, you'll be in a position to solve most of the questions which will be related to these topics. Okay, that's why I'm putting a lot of stress over here. So now coming back to the discussion, so the electronic wave functions deep inside the crystal, which is basically attributed to the different bands that is given by now. So once you were done with obtaining the energy eigenvalues, you can basically also next calculate the eigenfunctions as well, right? Because this will give you all the the rough idea of the probability. I mean, after all, we all know, I mean, how we can explain a particle, basically a wave or something like that. So this is quantum mechanics, right? You cannot do anything without having some information on the wave function as well as on the energy eigenvalue. So once you are given with some kind of potential profile, you should be in a position to get the energy eigenvalue as well as the energy eigenfunction, right? So from that you will, I mean, then half of the, not half, like 90% of the job is done. Then you are okay to do some other calculations. I mean, you can basically play around in the system. So this importance are very much required at this stage. So this is attributed to the different bands that is given by this. So where C is the normalization constant near the surface at z equals to 0, the bulk solution has to be fitted to an exponentially decaying solution, which is compatible with the constant V naught. Okay, constant V naught. So yes, I naught equals to, as mentioned, the exponential of minus square root of 2m h square times v naught minus e times z. Okay. So it can be shown the matching condition can be fulfilled for every possible energy eigenvalue, right? Which lies. can be shown the matching condition can be fulfilled for every possible energy eigenvalue is in the allowed band. As in the case for metals, this type of solution standing blockways extending into the crystal which spill over into the vacuum at the surface, right? So a qualitative plot of the wave function is shown in the figure 2. If imaginary values of k are considered like, I mean, that is k equals to minus I times q for z less than 0. Okay, and one defines this, I mean, well, immediately after that, once one will obtain this thing, which is I times sine of 2 delta equals to minus I h square pi q by MAV. So one obtains solution with a decaying amplitude into the crystal, which is given by this equation. So the energy eigenvalue then will be given by this equation, right? So E is real for the large negative Z as required. Also in the range of 0 less than Q and less than Q max. Okay, Q max is basically MAV by pi h cut square. So all the energies of the surface states fall into the forbidden gap. The complete solution is again found by matching the bulk solution to the exponentially decaying vacuum solution, right? So the result is a state localized at the surface, decaying both into the crystal and the vacuum. So the qualitative plot is shown in figure 3. Okay, that you can see. So it is for any standard semiconductor. What happens like this is the Fermi level, this is the Church neutrality location. In the conduction band, this is the valence band, donor state, acceptance state. Okay. So now I'll basically discuss you the regarding like this is the most important part. So this will be like your Schottky barrier junction, metal semiconductor junction. So this two part. So let's discuss this. So would like to basically introduce different type of junction, which is very important. So the junction is between a metal and a semiconductor. So in previous case, we have seen, also know we have taken like second. So in previous case, as you have seen, you have taken a p-type semiconductor, n-type semiconductor, and we have understood what happens, right? Now we'd like to replace one of the semiconductors with a metal. That's it. So this is the metal, and this is metal, this is semiconductor, this is the junction. Okay. So now let us say we can look at, let us say interface between the metal and semiconductor. So p-type semiconductor or n-type semiconductor, whatever. So what happens in that scenario? Okay. So this type of junctions are also known as Schottky junctions.
I mean, divided between metal and semiconductor. These are called Schottky junctions. So, or we could also call it Schottky diode. So we'll see how the Schottky diode behaves. So based on our understanding of materials so far, what do we expect? So that will be the topic of discussion. So when we have an interface between, or let's say junction between a metal and semiconductor, we have understood the semiconductors in quite a bit in detail so far, right? So the valence and conductance ones we have, then there is a Fermi energy. So what happens in metal? So this is also this has been discussed in our earlier session. So we said that there is also even in a metal there is going to be a bonds. So but in case of metal the Eg is right is very small. For metals this energy band gap is very small. Almost the conduction band and the valence band will be overlapping to each other. This is one of the scenario. And the metals band gap is very small, or we could also have a overlap as I mentioned, but for semiconductor, this thing is different. We have a large number of electrons in the conduction band in the outermost band. This is that as a characteristic of metal. So because of the presence of large number of electrons, uh, they are very good conductors. They are considered to be very good conductors. This is what we have studied in the introduction. Right. So the number of electrons like is very large. Now what happens when we bring these materials together? Then it will be interesting. So how can we analyze it? Okay, so to do that, we need to introduce a few more concepts. Definitions rather. This is essentially how you know the this is the bands will look like. Let us say there are two materials which are separate, not connections, so they are separate, and the metal is this part. Okay, going to the Fermi level, which you have already seen. Okay, and there is a parameter we'll call as work function of the metal that determines how much energy is required to take an electron. Okay, from the metals to outside the metal. Let us say you can refer that energy. Uh, Vacuum level. Okay, is the work function. Is the reference level for the vacuum. So the electron will completely becomes free here. So it can freely move about. So that is the reference level. So related to that, you know that you want to take out an electron from the metal into vacuum level. This much of energy up to spend here. Okay. So this is also known as work function. I mean, here we are representing the work function in terms of the voltage by M. Basically, it's referred in this way. So the charge time, the voltage, it's basically the energy. So that much of work is needed. How many like electrons you can take out? So various metals have a various work function depending upon the configuration. So they are not uniform. For example, here in the table you see this table if you see for the different work function for some of the elements like silver, aluminum, gold, and so on. So then the largest I'm seeing is 5.65. That's for platinum, right? For metals, typically it ranges from 4 to 5. This basically lie in this range only for metals. The important ones are the aluminum, which we use routinely in the semiconductor industry. So, and also we use tungsten sometime, okay, and a few other materials, of course, right? So you see that there are this, this are the units here in the electron volts, charge time voltage, it will give you the energy, which is very important characteristics, and there is nothing much we can do about this. So when you deposit a material, let us say aluminum, you are depositing, we get a certain work function. It also depends on the deposition condition and so on. Okay, so for example, if I deposit aluminum into different chambers, with two different techniques, let us say, then the work function may be slightly different, right? But these are something that, can be determined experimentally as well. And the other uh, variable, or rather parameters, that we want to define is known as electron affinity. Okay, so electron affinity essentially, it's defined for a semiconductor here. This table, follow this table. So the electron affinity is a measure of how much energy is required to capture an electron and convert the semiconductor into a negatively charged ion. That is the electron affinity. So in the bands, you can show electron affinity as basically the amount of this one. Okay, E Phyiscs. E chi. So the amount of energy required to capture an electron. So here, this is the electron affinity, E chi. And create a negatively charged ion, whereas the work function was amount of energy required to free an electron. Here you have to add, and there you have to reject. So essentially, in semiconductor, electron can be present in a conduction band, that is enough. So that is the electron affinity of this distance here that has been shown. E chi. This is known for a material. For example, the crystalline silicon will have an electron affinity of 4.01. Okay, so other materials have different amount of electron affinity, right? So it varies from material to material. Now we can also define a work function for semiconductor, because semiconductor also has a certain Fermi energy. That's pretty much obvious. And then you can remove an electron from that to, the free vacuum level. So this phi is basically like is the work function of this one, phi is from the Fermi level. I'll make a semiconductor short form S, and semiconductor, so I'll call it semi C. Okay. So the work function of a semiconductor Phyis is going to be the electron affinity plus the Fermi energy. So Phyis will be equals to chi plus EF. Okay, it's very important. So this is amount of the work function. Please write it down. Phi is equals to chi plus EC minus EF. Okay, how much it's away from the conduction band. So chi plus EC minus EF it will give you the work function for the semiconductor. It's a kind of N-type semiconductor. Okay, that's why Fermi level is lying here. It's just the donor level. Okay, you know once you have a silicon, the electron affinity is always going to be 4.01. So it's crystalline silicon. So I think it's much better known. Okay, so now this is when the semiconductor, the metal and the semiconductor far apart. So now if they brought in contact, what happens? That's on. Then the junction will be formed, right? There are no like the surface, the surface scattering and all that. So it's a good contact if you make. What happens? To understand, we'd like to draw this diagram. I've already drawn all these things, and so let us say we have a Fermi energy level. Okay, I see here. We're taking a semiconductor, which is let us say N-type semiconductor. We are taking this is conduction band, the H, and this is the for the valence band. Okay, and this is your Fermi energy for the semiconductor. This is for the metal. Now the question we want to answer is what happens, right? So we have brought this metal and N-type semiconductor into the contact. So semiconductor into contacts, what happens? Well, the Fermi energy is essentially a measure of, the energy, right? And that high, this probability, it is an energy level at which probability of finding particle is electron is high up. So essentially, so that level you could think as of, so if the temperature is high, it is going to smear out. The smearing out is given by the Fermi function, right? So essentially, you could think of it like a water tank. That's the analogy we can use. Now, what happens is the Fermi energy of the semiconductor is higher, so there are more electrons there, and on the other side, the electron energy is lesser. So what you can have basically an electron transfer. Okay, from this side to this side. This is possible. So will there be any hole transfer? This is an interesting question. Please listen carefully. And will there be any hole transfer? Well, I mean, there are no holes here. Okay, I mean, the majority carriers are electron, and there are a few holes, but you have electrons at much higher energy. So we talk about the current and we'll see what happens to the holes. Okay, so there will be any transfer of dopants because of after all we are taking, the same conductor. So you have a lot of electrons, and we say that electron transfer. This is the first thing we will accept the electron transfer from uh, semiconductor to the metal because semiconductor Fermi level is higher. Will there be any dopant transfer? You should be able to answer this by now. But there is not going to be any because transfer because the dopants are essentially fixed ions. Remember always, whenever you are doping semiconductor with replacing a silicon atom, like a phosphorus or inside some semiconductor, it's going to be phosphorus. It's a p type, which will be boron. So these are fixed to the lattice. The dopants are fixed, so they cannot be transferred. This is very important. So we'll always have only electron transfer. Well, is it possible that there is no energy, no transfer of electrons? The third situation. Okay. But so is it realistic? There is going to be electron transfer. Okay, fine. So electron transfer happens from semiconductor to metal. So will it make any difference to the Fermi energy? Well, at equilibrium, we have studied that in a device, the semiconductor, the Fermi level has to be uniform. Okay. So to draw the band diagram for a metal semiconductor, you know the Schottky diagram. We'll take the Fermi level to be uniform, which will have done multiple times already now. Okay, so once we do that, we know that you know the Fermi level will uniform, and there are these are the like lots of. Let me draw it. We know that you know the Fermi energy level, the uniform and metal. Will be uniform and metal. There are like lots of electron. It's not going to be changing much. So what happens to a semiconductor? Well, away from the junction between metal and semiconductor, it's a bulk semiconductor. It's not going to be changing its properties. So away from the junction, you need to have the conduction band and valence band similar to the this separated case. But as we approach the junction, what happens? We have taken some electron from semiconductor, right? And transferred them into the metal. So because of that, they are going to be some dopant atoms which will become space charge, right? So this is an n-type semiconductor. If you remove an electron, you will be left with a positive charge, right? So essentially removing the electrons means what happens to the dopant concentration? Sorry, the electron concentration reduces at the interface. So how do we represent reducing electron concentration? The Fermi level is going to be away from the conduction band, right? So expect that the Fermi energy moves like this. So basically here the distance is large, so fewer electrons than bulk, right? This what because electrons have gone into the metal, then this so it does bend further. I mean, you can look at it whichever way you know bands bend upwards. So I could even say that this is the opposite case, right? What is that? Yes. The semiconductor is depleted. All right, so we understand what happens to EC. What happens to EV? Okay, will it bend in this way? Is it possible? It's not right actually. So because we know that band gap cannot change, so this cannot be possible. So what happens to EC? Your EV will be parallel. Okay, I mean this is what it's going to be like this, like this. We have been following the previous cases. So number one, just draw the line. Okay, the equilibrium Fermi level, which is uniform, right? Uniform across this device because there is no external bias. When you apply the external bias, I mean, number two, look at, the electron transfer. So determine the electron transfer and draw the EC appropriately. So we'll see an accumulation. But right now it is depletion, right? So electron transfer and draw EC appropriately. Then draw EV, maintaining EG. That is it. And once you do this, this is the Fermi level. So this is this thing. This is a band diagram of Schottky junction. Okay, so now is there any field in the device? Right. Is there any built-in electric field? So you should now answer that. So there is definitely because there is a certain gradient, right? So it is indicative of an electric field present in the device, that EC, right? So now let us, this is the diagram, which is, much neater than what I have drawn. This diagram, okay, showing the same thing essentially, right? Because you have the bending as the way I have. Please look at this diagram over here. So we'll also define something. So this height basically, it's a Schottky barrier height. This is an important parameter. This is called the Schottky barrier height. So why is it a barrier? Well, you have electrons in the semiconductor and the field pointing out in this direction, right? So electron cannot cross that field. This path. Electron experience the barrier. Electrons cannot move into metal. Similarly, metal electrons cannot come into the semiconductor. So there is a barrier is given by phi b that you can see this much of energy, the amount of energy. So you can basically phi be simply going to be the work, simply going to be the work function of metal minus the electron affinity of the semiconductor. So by the way, this is ideal. Okay, we'll mention how this can change a little bit. So this is not easy parameter.
So what happens? Please remember this formula. This is very important. This is the ideal condition. So we want to determine, of course, whenever there is an electric field, so it's going to be depleted. There is a going to built-in potential. So how do you do that? We'll follow the same recipe. So the first step is always to draw the space charge. Okay, to know the Gauss's law, then you can determine the electric field here. So how this space charge is going to look like? In this case, we say that we say that electrons are moved from the semiconductor, so they should acquire the positive ions. So this is going to be uniform semiconductor. So it's ND, and this is going to be, let's say, at some x distance. The depletion region has extended the distance of nx. Same. So the crucial difference from a metal semiconductor junction and the regular PN junction is that the balancing charge. Okay, so this is positive charge over here. So the balancing charge is going to be occurring at the interface itself. So it's like a delta function. So, so it is like you know that the delta function essentially change at, like it's like so why is it a delta function? Well, it is a metal. So there cannot be any electric field in the metal, right? Because the charges, they will neutralize the electric field. So whatever electric field is there, that has to be like, it has to be whatever number, you will calculate the amount of electric field. So, and the amount you get in the material, it has to be zero. So the difference in the electric field is the surface charge. So that is going to be present. And that surface charge. So let us say my semiconductor has, let us do that the field, and then I will explain this one more time. So for now, it's a balancing charge. So this charge uh, Q, and is going to be minus N Q N D X N. Okay. So once you have this short of electric field, what happens? Sorry, sort of charge distribution. We are going to have the electric field. You can calculate the dx equal to the uh, right equal to the q by d epsilon. So this is d dx and q n d by epsilon naught for silicon. That is the epsilon for the silicon. So calculate the value of xi. It's going to be a linear function. Okay, the electric field. So this is the shape of the electric field. Okay, at xn it is becoming zero. Please remember this formula. It is very important. So this is xn, this is 0, and so what you see, there is a sudden jump. Okay, so you not you can say the right at equals v at 0. I could refer this line to be equals to 0. So once you have the electric field, you can easily calculate all these things. In this case, built-in potential is going to be simple. So this is my built-in potential. So you just need to integrate. Okay. It's going to be half times. I'll take, my built-in potential formula. Please remember this is QND by epsilon silicon times Xn square. So this is quadratic. So same as PN junction. So that is why you could also write you're showing this as a built-in potential over here, this part, basically. So there's going to be a band bending. So bulk is going to be this much difference in the built-in potential. So it can be given by this equation. So PBI is going to be like this. In this case, the Schottky barrier height is PB naught. So as I mentioned, please put this formula over here. So basically the Schottky barrier height is pi B naught minus EC minus EF. Okay. The fine is essentially the distance between is fine. I mean EC and EB. So this is the definition we are using in the figure here. So you have this built-in potential. One of the characteristics of built-in potential is that uh, it is quadratically dependent on the x, and we define it as a like n to be equal to w in this case. So it is a depletion region is only in the semiconductor, not in the metal, right? So xn is equal to w implies w is equals to square root of 2 epsilon I, 2 epsilon silicon by QND times PI. So this is for the with depletion extent. So this is how the metal semiconductor junction is going to behave. This is very, very important. Okay. So this is without the applied voltage. What happens when you apply a certain voltage? With applied bias, same story as PN junction. Okay, whenever we are apply a positive bias, let us say what will happen. We are considering, let's say, we're applying a sort of a structure. This is a square, and I'm applying a voltage. This is applied voltage VA. Okay, this is metal, this is semiconductor, and this metal semiconductor junction. So this shortcut has been formed with the line. So VA is positive. So this is your junction. When V is positive, Fermi level lowers, right? When V is negative, Fermi level go up. So V is greater than zero, the V, I mean, when V is less than zero, the Fermi level is going to go up, and it is less than zero. So in a way, you could think of, you keep the EF in the bulk of the semiconductor as constant, or you hold it fixed and you move the EF in the metal. So if you're applying positive voltage, the whole the band. So this way you can also show that, let us say I'll make the EF in the for the case, I'll draw the Fermi level in the semiconductor EF, and I'll pull the metal semiconductor level lower than the extent of the applied voltage. So this is going to be my this EF Fermi level. This is for the metal. Now we did that. So essentially, what we are doing is we are pulling the bands down. So the barrier height is going to reduce. Okay. So instead of the previous case, we will have a barrier which is like this, like this. Okay. So you will still okay. Yeah, this is now essentially because we are pulling it down. So here we are essentially reducing the depletion region. So the depletion is reduced here. So another way to think about it, essentially, we are putting positive charge on the metal so that on the metal, so that it is going to pull electrons towards the interface, right? So you have the Fermi level, the bands are going down. Okay, so this is what happens when you have positive voltage. Okay, this is for VA greater than zero. This condition is for VA greater than zero. So essentially the VA is going down. So, okay, if your VA is less than zero, then the reverse happens, this condition. Okay, so the same story, we draw the EF, the semiconductor of the semiconductor. Okay, take the EF metal to be somewhere, EF of the metal to be higher. Now we are actually, like, this is the formula for the metal. Okay, so this is okay. In a way, I'm applying upon the negative voltage, right? So this is your UVA, the difference. You are pulling it up, right? So in a way, you are repelling the electrons from the junction. So you are not helping that process of electrons at the junction. So what happens now is you will have the barrier which is stronger like this. So the depletion this much. Okay. And like this. So it has been increased this now, right? So the barrier is stronger, or rather built-in potential is larger. Okay. This is very stronger. So the built-in potential was essentially this range. Okay. This So this is V plus now the I mean, we are applying the voltage, but this is actually negative. So the VBI minus VA. Okay. So the whole thing is has been increased, but here it's minus, right? But VA is positive. VBI plus VA. So the built-in barrier has been increased now. So this is how the band will change. So I'll stop it here and move to the next topic. I'll quickly go through some of the heterojunctions examples. So basically, I'll recall how to draw the band diagrams for heterojunction, p-type, n-type. So this is just some of the basic things you should know. Okay. So different kinds of band arrangement that are possible. So let us come to the whiteboard again. So I'm trying to say here is that you have a gallium arsenide, you have a band gap of 1.4 electron volt. Okay. You have support gallium arsenide and band gap of aluminum arsenide. So band gap of 2.2 electron volt. So it's abrupt heterojunction like gallium arsenide and aluminum arsenide. So you can say aluminum arsenide, this one. So it's an abrupt heterojunction, abruptly changing here. So this is that's we are putting a lot of stress in the junction because junction the property actually changes, right? Abruptly. That is why it's very important to rather know about the junction property, right? So that is why we are putting so much of stress over here. So over that you can do instead that is you can actually grid one second. Yeah, this is the grade. So when the grade I change, that what do I mean by change? I gradually change the composition. Okay. So I gradually change the composition over here. Instead of abruptly, I gradually change the composition of say gallium arsenide. Uh, this portion. Okay. So this is X and this is one minus X. I slowly change X because of this. There is a very gradual change. So there are higher properties like a band gap and all these things will change based on this thing. So the band gap will gradually will be changed now. It's EG. Okay. So other things like maybe electron affinity, dielectric constant, the things will also change. But most important thing is that your band gap will actually change because of this. So this has huge implication in the practical devices that are used. For example, in white LEDs, your transistor that are going to into your cell phones for RF transmission and receiving modules. So those are made of indium phosphide, gallium arsenide, sort of HMT that we'll talk about. So you use gradual change in the grading and it's actually used in the commercial devices. That is why it's very important. So essentially what is happening is that you are taking, say, for example, aluminum. Okay. So aluminum gallium arsenide where it's X and this is 1 minus X, you are gradually changing X. Practically, this is 1 minus X and you are growing basically if you are changing this. So suppose I have a layer of what is happening practical is that this is, let's say this is gallium arsenide. Okay. And when I try to grow on top of this using a technique like MOCVD and MBE, the growth parameters that can be changed, right? This is very important. How we will deal with the growth parameters during the deposition. So I gradually start increasing the aluminum fraction, maybe the aluminum source of aluminum precursor or whatever I'm using, I can gradually increase it up. So practically what it means is that maybe I can use the aluminum cell in MB. So more aluminum will start gradually coming. So slowly and slowly I keep growing up thickness. This thickness is Z axis. Okay. So by the way, all the way up. So I'll start increasing. Suppose this is 100 nanometer, this much thickness. Suppose I'm going to deposit 100 nanometer thick this part. So that I'm gradually increasing. So aluminum say percent, I mean 100%. So what is happening here is that throughout time the aluminum percentage is X is gradually increasing. The, the band gap, you have to make sure at this point your band gap is on the gallium arsenide. Okay, this portion and the which is 2.2. So over this your band gap is gradually increasing. This is what happening is that the aluminum arsenide which is 1 point band gap is 1.4, and suppose this is your aluminum. Okay, this has a band gap of 2.2. It's gradually changing now. So it is changing like this. There is no abrupt heterojunction like this. You have, so we take the slope. No, you have an electric field. Okay, remember this. I already discussed. By the way, this is for the electrons actually. For holes, it will be the slope of this thing. So the valence band, and we always only write the conduction band because of the band gap typically. So we always historically have been taking the band gap as the same. Okay. There is a slope in the conduction band, as you know. Then I say the slope of the conduction band gives to the field. Okay. So instead of this structure, for example, I'll have a structure like this, like a bending. So the band gap same as the AC. So then your field will be different, and because the field is different, your acceleration, like your effective mass will change, experience different kind of potential. If you have a linear gradation like this, okay, then the electric field is constant and it will move like this. But then I'm talking about the same material, by the way. The same material is this like silicon. Okay. I have a band, I have an electric field goes like this. It's a bending. Okay. This is how EC and EV goes. In case your conduction band is changing in an exponential way, then your dx also like it's no longer constant. Okay. This will also change exponentially. So here the field is going linearly. here in this case, and here it's changing exponentially. Here the slope is constant, here it's not. This is very important thing. The field is also exponentially changing. So an electron will take the different amount of time to go to this point compared to this here to here. Okay. So depending on your grading. So and the way you practically grade this kind of thing is that you increase the aluminum composition. By the way, then it's not graded. This is not graded. This is only constant material, but with the heterojunction, you can actually grade it and make it even more. You have more flexibility for this case. Okay. What I mean by that is that when you are grading linearly, suppose you have something like uh, so this is aluminum arsenide, for example. Okay, this is gallium arsenide. This is aluminum arsenide. This part and this part we're forming the heterojunction. Might have another where it's just a grading. There's a field. So this is constant field. Okay, this part is constant field. Look very carefully, huh? So this field is the slope of the conduction band. The conduction band has a different slope and the valence band. This was not possible in a silicon short of thing right here. Slope are different. So all it depends on the slope. So how the band curvature is. So in that way we define all these things. So but now I'll come to this portion. Okay. So here what happens? Changing. There will be a layer of undoped gallium arsenide. Okay. Now let's think about this situation. So there will be a layer, thin layer of undoped aluminum gallium arsenide. This one. Okay. Of the same composition as this is if it is 30%, this will be also 30%. So this aluminum gallium arsenide undoped and 2D electron gas is actually formed uh, at this interface, okay, of the undoped gallium arsenide. Sorry, this interface of undoped aluminum arsenide and the gallium arsenide. So this doped gallium arsenide and this is doped by DOA. Okay. So this doped gallium arsenide and this doped aluminum arsenide, sorry, and this is undoped gallium arsenide. This one. So between there is a thin layer of undoped gallium arsenide. This background impurity of this will not be physically coexisting with the channel here. So the band diagram, if we draw the band diagram, it will look like this is a Fermi energy. Okay, the Fermi level, the Fermi energy level. So what will happen is that it will look like this. This initially look like this. So the valence band will also have a mimic there. So essentially, this is the doped in minus aluminum gallium arsenide. This layer on the top. Okay, this layer is undoped layer, and this part to very few nanometer, maybe 5 to 10 nanometer. This is undoped aluminum gallium arsenide, and this is gallium arsenide layer. This part gallium arsenide. So of course, this is your delta EC, which is conduction discontinuity. In a way, if you have the like, so if I draw a next slide here, one second. So this is your, uh, so essentially what will happen is that, so this is your Fermi level. Okay, what will happen that is a conduction band. This one, okay, like this black color line. The valence band will also look like this. This valence band will exactly look like this. So this is your Fermi level. Okay. So this part is your N minus doped aluminum gallium arsenide. So here aluminum gallium arsenide, this part is a few nanometer. This undoped is the Dirac delta of EB. This part only. Okay. This is delta, and EC is the conduction band, and this is your conduct. The Fermi level is actually above the conduction band. Okay, here, this part. So this part has a high density of 2D electron gas. This part, and 2D electron gas that has formed physically because of this layer, they are donors now. This part. So they are donors here because we have low. So these donors will donate electrons. Those electrons will essentially fall here, this side, and electrons will fall here and create this electron gas. This is what a Fermi level has gone below the conduction band and or above the conduction band. So band electrons are falling here. So, but there's a layer, it's a special few nanometers. Special layer makes sure that this electron gas, this channel, this is the channel, this part. So physically they are separated from the dopant layer. This is the dopant layer. It's physically separated from the dopant layer. This spatial will make sure that this will separate from the donor, the spatial layer. So the scattering will be low. Okay. The scattering will be low, which means that the mobility will be very high, right? Mobility is very high, scattering low. So this mobility will be very high, and so call it as a high electromobility transistor. So I told that the room temperature you can possibly get around 18,000, like 8,000 centimeters per whole second of mobility. This is beauty because you are actually having an expectaxial interface. So the roughness, interface roughness scattering were negligible of that, and your doping is the electron they're physically away, separated by a few nanometer by the spatial layer. So they will donate, keep the electron, and a few nanometer spatial layer will make sure that scattering that the channel charge is not coexisting with the dopant because the gallium arsenide is not doped right in this portion. So this is the basic structure of gallium arsenide, aluminum gallium arsenide high electron mobility transistor, HMT. So this is very important topic. You should understand this very carefully.